Calorimetry measures heat flow in a chemical reaction. Heat is not a form of energy, but a transfer of energy. In a typical high school science classroom, calorimeters are devices that measures this heat flow. It is typically made up of 2 styrofoam cups and a thermometer. Substances are added into the cup and mixed, and temperature changes are recorded. If a chip or nut is burned, we could calculate the amount of energy released by using water. The energy released by the nut or chip will be completely transferred to the water. If we know the energy absorbed by the water, then we know the energy released by the nut or chip. We can calculate the energy of the water because we know all the constants for water. This is a general diagram of a heating cooling curve of any substance. The only difference is the diagram may be taller or shorter. It might be wider or narrower. It depends on their melting, freezing, and boiling point. The vertical axis is labeled temperature, which is proportional to average kinetic energy. The horizontal is labeled time, potential energy, or heat energy. The diagram that I provided is for water because 0 degrees Celsius is the melting and freezing point of water. 100 degrees Celsius is the boiling point of water. So in this diagram, any point below 0 degrees is going to be solid. At this point, we're going to start with solid ice. And in this process, if we go to the right, we are going to be melting, and we are also going to have liquid. From 0 degrees Celsius to 100 degrees Celsius, we are going to be in the liquid state of matter. At this point here, since this is 100 degrees, we know water is going to start to boil. So we're going to start with liquid, and it's going to start boiling, and it's going to become gas or steam. So at the second plateau, we are going to have both liquid and gas. And as we reach down here, this is all going to be gas, steam, or vapor for water. This is pretty much true for every substance. It's just the temperature will change for the melting, freezing, and boiling point. So in order for a substance to change a state of matter, it must go through a phase change. So in the first plateau, I am going from a solid to liquid. To go from solid to liquid, I need to increase my potential energy or heat. So in this process, since I'm adding potential energy or transferring heat in, so the phase change here is melting, or in the opposite direction, we're going to remove potential energy. So this is going to freeze. At 100 degrees, as we keep on adding potential energy, it is going to vaporize. And as we move heat, this is going to condense. You can also go from solid to gas. When we go from solid to gas, that's called sublimation. Since the substance has such a low melting or freezing point, it's going to immediately sublime. It's going to go from a solid to a gas. Example of that is dry ice. In general, you do not see a liquid phase for dry ice. Opposite of sublimation, gas to solid, is deposition. This is similar if you have an old refrigerator or your siblings go to college and they have those cube refrigerator. The freezer accumulates ice, so you have to defrost it every once in a while. That is because when you open the freezer, gas molecules go in. As soon as you close it, the temperature drops really rapidly, so there's no liquid phase. It goes from gas to solid. Each substance in general has 6 phase changes: sublimation, which is solid to gas; deposition, which is gas to solid; melting, which is solid to liquid; freezing, which is liquid to solid. vaporization, which is liquid to gas, and condensation, which is gas to liquid. This is why at the plateau we have both states of matter. Also, if you notice, as I go from solid, liquid to gas, my potential energy or heat energy has to increase. So that is an endothermic process. So heat has to be absorbed. Endothermic process are positive. When I go from gas to liquid to solid, I need to remove heat. So that is an exothermic process, which is negative. From the graph, you notice during a phase change, the temperature remains constant. The only thing that has changed is time, potential energy, or heat. The reason the temperature remains constant is the added potential energy or heat, or the removal of the potential energy or heat, is used to overcome or strengthen the intermolecular forces that hold the molecules together. So if you notice, a solid has the atoms really close together, so the intermolecular forces are much stronger, the liquid is a little bit less, and the gases are very weak. As we stated earlier, since we know all the constants for water, water is an ideal substance to calculate the energy released by burning substances. In general, there are two main equations. When there is a temperature change, we're going to use Q equals mc delta T. So we know when the line is at a diagonal, there is a temperature change. Anytime the line is horizontal, there is no temperature change. Those are, if you notice, at the melting, freezing, boiling, vaporization, and condensation. When there is no temperature change, the equation gets modified and becomes Q equals MHF for the melting, freezing, and Q equals MHV for the vaporization, condensation. So the first equation, which is Q equals mc delta T, and in some books they don't use C, they will use S instead. Q stands for heat transfer or heat flow. It's usually measured in joules or calories. M is mass. It's usually given in grams. If it's given in moles, you need to use molar mass and convert it into grams. C is the heat capacity. The units is joules per gram degrees Celsius. However, it could also be in calories per gram degrees Celsius, because the units for heat can also be in calories. It could also be in joules per mole degrees Celsius, or calories per mole degrees Celsius, or the degrees Celsius can be replaced by kelvins. So what is C? C is the amount of energy required to change 1 gram of any substances 1 degree Celsius. Delta T, remember the triangle means change in. Its temperature change is T final minus T initial. And we know that temperature could be in degrees Celsius or Kelvin. The other two equations look very similar. Q equals MHF and Q equals MHV. Q still stands for heat, like in the previous equation, measured in joules or calories. M is mass, can be given in grams or moles. HF is latent heat of fusion. It is the amount of energy required to either melt or freeze a substance. HV is called the heat of vaporization, and it is the amount of energy required to release or add to vaporize and condense a substance. C, HF, HV are constants. They will be provided for you. If it is not provided for you, you must solve for it. The other equation you will see sometimes is called bomb calorimetry. Bomb calorimetry is an ideal device that when substances are burned, none of the energy is released to the surrounding. It is absorbed completely, 100% by the water inside the bomb calorimeter. If a bomb calorimeter is provided, the equation is Q equals C delta T. We don't worry about the mass because the volume is constant. C for the bomb calorimeter must be provided in order to calculate this. Other important concept that you need to note when you are calculating heating and cooling curve is where the temperatures and the states of matter are located. 0 degrees ice is at the start of the plateau. Remember, below here is solid at 0 degrees. This is the highest temperature that solid can exist, ice. As heat is added or potential energy is added, the solid ice starts to melt and become liquid water at 0 degrees because again, we are still at the flat line. So this is 0 degrees water. Once we reach 100 degrees Celsius, here is the last state that liquid water exists before it starts to be converted into gas. So here we're going to have liquid, and the liquid is going to become gas. At the end of the plateau, all the water in the liquid state is converted into steam. So right here we have 100 degrees Celsius steam. You need to memorize where the temperature and the states of matter is located. This also applies to any other substances. The only thing that changes is their temperature, is their melting, freezing, boiling point. For calorimetry that is not integrated with other topics, you will typically see 3 types of problem. The easiest one is the one step. You either use Q equals MC delta T or Q equals MHF or MHV, plug in and solve for the unknown variable. The second type is a multi-step problem that uses more than one equation. And the third type is a mixture problem in which one thing is added to another. So one will be at a hotter temperature and one will be at a colder temperature, and they will reach thermal equilibrium. So the hot one will release and the cold one will gain the same amount and they will reach the same temperature, final temperature. Let's look at the first example. If you don't know where to begin, identify the variables. If you identify the variables, the equation will come out. So we have 445 grams. We know that is mass because the units are grams. So M is 445 grams. At ice, negative 58 degrees Celsius is heated until it reaches. So it went from 58 to 29. Since it went from this to that, the from is the initial temperature, which is negative 58. My final temperature is negative 29. This substance is ice, so I need to use the constant of ice, which is on your table, which is 2.02 joules per gram degrees Celsius. Find the heat, which is Q. The only equation that I know that has these variables is Q equals MC delta T. And remember, delta T is MC, T final minus T initial. Now I'm going to plug in. My mass is 445 grams. My C is 2.02 joules per gram degrees Celsius. My T final is negative 29 degrees Celsius minus a minus 58 degrees Celsius. Since it's a minus and a minus right here, this becomes a plus. So this is negative 29 degrees Celsius plus a 58 degrees Celsius. So if you do the math correctly, you get something like this. Now we need to do sig figs. 2958. If I line it up, I'm going to line it up here. So my temperature, there's 2. Constants does not count. My mass has 3, so my final answer has 2. 1, 2. I look 1 to the right. This becomes 2.6 times 10 to the 4th units of joules. We have a gram on top, a gram on bottom that they cancel out. We have a degrees Celsius on the bottom, degrees Celsius on top. So what we have left over is joules. This is number 15 in your worksheet. What is the heat capacity of silicon if the temperature of a 4.11 gram sample of silicon is increased by 3.8 degrees Celsius when 11.1 joules of heat is added? So the first thing you want to do is identify the variable. We know we are looking for C. 4.11 is the mass because the units are in grams. It is increased by 3.8 degrees Celsius, so that is a temperature change. That is not initial or final because it told you it increased. 11.1 joule is added, so we know this is an endothermic process, so we know the Q has to be positive. So the only equation with these variables is Q equals mc delta T. At this point, if you're struggling with Algebra 1, solve for C. To isolate C, we need to divide both sides by m delta T. So the m cancels out and the delta T cancels out, so C becomes Q divided by m delta T. Now plug in your numbers. Q is 11.1 joules divided by m, which is 4.11 grams, divided by 3.8 degrees Celsius. So C becomes 0.7107. Now we need to do sig figs. Mass has 3 sig figs. Temperature has 2 sig figs. The Q has 3. Since we're multiplying and dividing, it is the least amount, so we need 2 in our answer. Starting from the left, we go to the first non-zero digit, which is a 7. 1, 2. I look 1 to the right. Since it's less than 5, the 1 stays. So C becomes 0.71. Now we need to use proper units. On top there is a joule. On bottom there's a gram multiplied by a degree Celsius. So this becomes joules, grams, degrees Celsius. This is number 16 in your work packet. Pause the video, solve the problem, and then check your answer. How much heat must be added to an 8.21 gram sample of gold if temperature is increased by 6.2 degrees Celsius? They give you the constant for gold as 0.13 joules per gram degrees Celsius. So first thing you're going to do is identify the variables. 8.21 grams we know is mass because the units are grams. The temperature increase, again, delta T is given, not T final or T initial. 6.2 degrees Celsius. C is given as 0.13 joules per gram degrees Celsius. And we're looking for Q. Only equation with these variables are Q equals mc delta T. We will plug it in. This is going to be 8.21 grams multiplied by 0.13 joules per gram degrees Celsius. Temperature is 6.2 degrees Celsius. If you multiply all the math, Q becomes 6.61726. Now we need to do sig figs. There are 3 from the mass. There's 2 from the temperature. Constants do not count, so my final answer needs 2. I start from the left to the first non-zero digit, which is a 6. 1, 2. I look 1 to the right. Since it's less than 5, it stays, so this is 6.6. There's a gram on top, a gram on bottom. It cancels out. We have a degree Celsius on top, a degree Celsius on the bottom, so the only unit left is joules. Heat is measured in joules or calories. This is 18C in your packet. Determine energy required to boil 0.325 moles of water at 100 degrees Celsius. Since we're boiling and it's at 100 degrees Celsius, there is no temperature change. This is going to be a phase change. Since we are boiling, the equation that we're going to use is Q is equal to mHV, which is the heat of vaporization. We have the mass, but the mass is given in moles. And we could look up HV, or heat of vaporization, in the table that I provided for you, and it's 2,256 joules per gram. We can't just multiply these through because HV, the units are in grams, and the mass is given in moles. So we need to convert either the moles into grams or grams into moles. To convert moles into mass, we're going to use molar mass. Remember, molar mass tells you that 1 mole of a substance X is equal to its mass in grams off the periodic table X. So we're going to start with 0.325 moles. The substance here is water, so it's H2O. Diagonal units have to be the same. Moles, H2O. There are 18.02 grams of H2O in 1 mole. This is multiplied by HV, which is 2,256 joules per gram. This is equal to 13,208. Now we need to do sig figs. This is a constant, does not count. There are 3 in my math, so my final answer has to have 3. I'm going to start at the left, go to the first non-zero digit, which is 1, and count 3. 1, 2, 3. I look 1 to the right. It is less than 5, so the 2 stays. So it's going to be 13,002. And we need to put zeros here as placeholders because the 2 is in the hundredths place. So we could rewrite this in scientific notation, which is 1.32 times 10 to the 4th units of joules. This is number 22 in your packet. Pause the video, solve the problem, and then check your answer. Here we're looking for energy. So we know we're looking for Q when 20 grams of water, so we know the mass is 20 grams, undergoes freezing. Since it's going freezing, that means this is a phase change. During a phase change, we know that there is no temperature change, so the equation we're going to use is mHF. We know the mass, we know HF because this is a constant that is on your table. The heat of fusion is equal to 333.6 joules per gram. In this problem, we don't need to do any conversion because the units are the same, so I'm just going to plug it in. So the mass is 20 grams. Heat of fusion is 333.6 joules per gram. 6,672. Now we're going to do sig figs. Mass has only 1. This is a constant, so my final answer has only 1 sig fig. I start at the left, first non-zero digit, which is a 6. I count, look 1 to the right. It is greater than 5, so the 6 becomes a 7. Since it's at a thousandths place, we need to put placeholders, because we want this 7 at the thousandths place. The grams on top cancels out with the grams on bottom, so the units left is joules, so it's 7,000 joules.